So, welcome to our continuing discussion on unidirectional transport in a Cartesian coordinate system. The conservation equation, we had reduced it by scaling. Okay. So, we had used the scales that T star is equal to T minus T naught by T1 minus T naught. Because of this, at the bottom surface T star was 1, at the top surface it was 0. And at initial time T star was 0 everywhere. Z star is equal to Z by H. Okay. So, the Z coordinate varied between 0 and 1 as well. And if we scale the time scale by the diffusion time, okay, we get an equation which I have written here, okay, which is independent of parameters, okay, which does not contain any dimensional parameter in it. The boundary conditions also do not contain any dimensional parameter in them. The boundaries are at Z star is equal to 0 and 1. The values of the temperature are T star is equal to 0 and 1 at the boundaries, and T star is equal to 0 throughout the domain. And we were examining a method to solve this problem. So, the first thing is to identify the steady solution. In the limit as T goes to 0, you would expect the temperature to reach a steady state, and that steady state solution. So, I had written the temperature field as T star is equal to a steady solution plus a transient solution. Okay, I had written that as a sum of a steady solution and a transient solution. The steady solution is independent of time. Okay. So, it just satisfies the second derivative is equal to 0. Okay. And from that and the boundary conditions you can find out what is the steady part. Okay. Now, how do I find the equation for the transient part? Take the equation for the total temperature, subtract out the equation for the steady temperature. Okay. Take the equation for the whole temperature, for the total temperature, subtract out the equation for the steady temperature, and I will get an equation for the transient part of the temperature field. Okay. Similarly, boundary conditions. Take the boundary condition for the total temperature, subtract out the boundary condition for the steady temperature, and you will get the boundary condition for the transient temperature. And in this case, we showed that at both boundaries, since the total temperature and the steady temperature have to be the same, the transient temperature has to be 0 on both spatial boundaries. At initial time, the temperature is 0 throughout the domain. The steady temperature is independent of time. Okay. And therefore, the transient temperature is basically just the negative of the steady temperature. So, the idea is that we have already determined what is the temperature at steady state. If we can determine what is the transient solution to the temperature, we can then use that in order to find out what is the total temperature as a function of z and as a function of time. Okay. So, these are the equations and the boundary conditions. Okay. And the method I will use is called separation of variables. So, I have a domain z star is equal to 0, z star is equal to 1, and as I said, if you plot the temperature as a function of time, okay, the temperature is T star is equal to 1 at the bottom, T star is equal to 0 at initial time, at the top surface at z star is equal to 1. This is the steady solution. Okay. Initially, you would expect the solution to be a step function because it is 0 throughout the domain and it is 1 only at the bottom surface. Okay. And as a function of time, this temperature field evolves as a function of time until it reaches its final steady state, and we would like to find out how this temperature field evolves in time by solving these equations. So, we will use the separation of variables procedure. Okay. I will write T star is equal to some function of t times some function of z. Okay. Write the temperature as the product of two functions one is only a function of time and the other is only a function of z. Okay. So, substitute that into the balance equation. Okay. So, this is the standard procedure that you use. Write the temperature as a function of time times a function of z, substitute that into the balance equation. Okay. And what I will get is that z of z times df by dt star is equal to f of t dz d square. Okay. Note that I am using capital Z for this function. Okay. I am using the symbol capital Z for this function. Okay. And I divide by f times z. Okay. Okay. Divide throughout by f times z. They will get 1 over f df by dt star is equal to 1 over z d square z by dz star square. Note that f is only a function of time and z is only a function of z star. Okay. The left side of this equation is only a function of t star, the right side is only a function of z star, and that means that both have to be equal to a constant. Whenever you have an equation in which the left side depends only on one coordinate and the right side depends only upon another independent coordinate, then both sides have to be constants. The reason is because if they are not constants and if I keep t the same and change z, then the left side will remain unchanged, whereas the right side will change and the equality is no longer valid. In this equation, the equality has to be valid for all time and all z, and therefore, the only way it will be valid is if both of these are equal to constants. What should be the value of this constant? Okay. So, you can see that on the left side I have an equation of the form 1 by f df by dt is equal to some constant. The solution for that is f log f. Okay, so, if I take t to the right side, I will get df by f c dt star, which means that log of f is equal to c times t star, which means that f plus a constant a, f is equal to a e power c t star. This is an exponential function, okay. Exponentially increasing if c is positive, exponentially decreasing if c is negative. Okay. This exponential function is a factor in this transient solution. Okay. This exponential function is a factor in this transient solution. Okay. As t goes to infinity, you would expect this transient part to go to 0. Recall, we had written the total temperature as the sum of the steady plus the transient. In the limit of long time, you would expect the solution to be equal to the steady solution, which means the transient solution has to decrease to 0. If this constant c is positive, the transient solution is exponentially increasing and therefore, it does not decrease to 0. The transient solution decreases to 0 only if c is negative, in which case you get an exponentially decreasing function. Okay. Therefore, the requirement that the transient solution has to decrease to 0 implies that this constant has to be negative, okay, that this constant has to be negative. Okay. Okay. It has to be a negative constant and therefore, I can write this as minus beta square. Okay. where beta square is a positive number and this solution is negative, and therefore, the solution is minus beta square. Okay. And that has to be subject to the boundary conditions T star transient is equal to 0 here, the homogeneous boundary conditions T star transient is equal to 0 here, and T star transient is equal to minus of 1 minus z at t is equal to 0. Okay. So, this is the equation. Okay. Both sides have to be constant. What should be this constant beta? Okay. So, we do not yet have we have not yet fixed this constant beta. Okay. So, let us first solve for the z, the function z. Okay. So, the equation for the function z is 1 over z d square z by dz star square is equal to minus beta square. Okay. Or d square z by and since the solution of this equation is sine and cosine functions. Okay. Now, let me just write the cosine function first. This is the sum of sine and cos functions. If you take the second derivative, you will get minus beta square times the same function. Okay. So these are the solutions for z. Okay. What is the constants a and b have to be determined from the boundary conditions. Okay. We know that at z star is equal to 0, transient is equal to 0, which implies that z has to be equal to 0, okay, which means that z has to be equal to 0, because z contains the spatial part. The function f is only a function of time. Okay. The spatial part is contained in z, and therefore, the boundary condition has to be satisfied by the spatial part, okay, that it has to be equal to 0. Okay. Beta times z has to be equal to 0, and beta is not 0 in general, right, because if so I am sorry, the okay, f times z has to be 0. F is only a function of time. Okay. If f was 0, then the solution would be 0 for all time. So, f cannot be 0, and that implies that z is equal to 0. Okay. The capital Z is equal to 0 at the bottom surface. Capital Z is a times sine of beta z star plus b times cos of beta z star. At z star is equal to 0, the sine function is 0, cos function is 1, and therefore, we get one condition, that is b equals 0. Okay. And once you apply this boundary condition, the solution becomes z is equal to a sine of beta z star. Okay. Now, there is a second condition at z star is equal to 1, t transient is equal to 0, right, and that implies that a sine of beta is equal to 0. Okay. At z star is equal to 1, a sine of beta equal to 0. This can be satisfied, of course, if a is equal to 0, but in that case capital Z is equal to 0 and you get a trivial solution. Okay, t is equal to 0, right, and that does not satisfy the initial condition. The other possibility is that sine of beta equals to 0. Okay. Recall that the sine function, okay, if I plot beta versus sine beta, okay, sorry, sine beta versus beta, okay, this is 0 at 0 and it passes through 0 at an infinite number of points, okay, 0, pi, 2 pi, 3 pi, etc. Okay. So, beta can assume any of those values where it passes through 0, okay, pi, 2 pi, etc. So, the most general solution for beta is that beta is equal to I times pi, where I is an integer, okay, where I is an integer. Okay. So, beta takes the general value I times pi, where I is an integer. Okay. So, there are an infinite number of solutions for this constant beta. Okay. So, I will refer to these as beta I. Okay. Okay. So, the most general solution for z is equal to sine of I pi z star, okay, times some constant, I will call it as a. Okay. This function satisfies the boundary conditions for any integer value of I. Okay. This satisfies the boundary conditions for any integer value of I. Okay. So, that is the solution for z. The solution for f, I have to solve the equation 1 by f df by dt is equal to minus beta I square. Okay. Which means that the solution for f is e power minus beta I square t. Okay. And since beta is I pi, I will get minus e power minus I pi the whole square times t. Okay. So, that is the solution for f, and the transient part of the solution t star, okay, has to be equal to the product of these sine of I pi z e power minus I pi the whole square t times a constant a. Okay. This solution satisfies the equations and the boundary conditions for any integer value of I. Okay. This solution satisfies the equations and the boundary conditions for any integer value of I. That means that the most general solution is a summation of all of these functions over all values of I. Okay. So, the most general solution is the summation of all of these functions over all values of I. Okay. That is the most general solution for this equation. Okay. I should note here that in this case I is going from 1 to infinity, because for I is equal to 0 the sine function is 0. Okay. So, in general you would take I is equal to 0 to infinity, but in this case for I is equal to 0 the solution is equal to 0. Okay. So, therefore, I have taken it from 1 to infinity. Okay. So, that is the solution for t. Okay. And this now contains an infinite number of constants a I, pre-multiplying the solutions sine I pi z star and e power minus I pi the whole square t. This solution satisfies the equation, the second order equation. Okay. This solution satisfies the second order equation, the governing equation. Okay. And it satisfies both boundary conditions, because we have ensured that capital Z is equal to 0 on both boundaries. Okay. By this choice of constant beta I is equal to I pi, I have ensured that capital Z is equal to 0 on both boundaries. what we have not yet satisfied is the initial condition. T star is equal to minus of 1 minus z star at t equal to 0. Okay. That initial condition we have not yet satisfied. Okay. So, at t is equal to 0, this is equivalent to the summation of I is equal to 1 to infinity okay. At t is equal to 0, at t is equal to 0, you can easily see that this exponential is just equal to 1. Okay. So, that exponential is just equal to 1 at t is equal to 0. So, the solution becomes t star is equal to this is equal to minus of 1 minus z star. So, it appears that we have just an infinite number of equations and just one constant. Okay. How do we solve this equation in order to get the solution? Okay. How do we solve this equation in order to get the solution? Okay. So, I will go through the solution procedure. It is called an orthogonality. Okay. Relation. This orthogonality relation is used in order to find out what is the solution of this equation. So, the way that I solve this is to multiply the left and right sides multiply by sine of j pi z star, where j is some other integer, where j is some other integer. So, I multiply the left and the right sides by sine of j pi z star, where j is some other integer. On the left hand side, you can see what you will get. So, let me write the procedure here. Integrate z star equals 0 to 1. Multiply the left and the right sides by this function sine of j pi z star, where j is also an integer, and integrate from 0 to 1. If I multiply the left hand side, let us see what I get. This is integral 0 to 1 dz star sine of sine I pi z star times sine j pi z star. I have to use the product rule. This is equal to integral dz star between 0 to 1 using the product rule. This is equal to half, this is an identity of cos of I minus j pi z star minus cos of I plus j pi z. Express the product of sine functions as the difference. Sine A sine B is cos is 1/2 of cos A minus B minus cos A plus B. So, that product rule we are using here. And now I can integrate this. Is equal to half integral 0 to 1 dz. So, I can integrate out these functions. integral of the cost function is going to be equal to sine of I minus j pi z star divided by I minus j pi. Okay. That is the first function. Integral of cos function, cos of a z is sine a z by a. The second one is sine of I plus j pi z, okay, by I plus j pi. Okay. Now, let us examine this carefully. Okay. I is an integer, j is an integer. Therefore, I plus j is an integer, I minus j is also an integer. The sine function of an integer times pi times z is 0, okay, because for all integer values the sine function of an integer times pi times z is equal to 0. Okay. So, both of these terms are 0. Okay. This is equal to 0 for I is not equal to j. Okay. When I is not equal to j, this is equal to 0 because the sine function is 0. When I is equal to j, this first term here is of the form 0 by 0. Okay. This first term here is of the form 0 by 0, and therefore, I have to take the limit of the numerator and the denominator going to 0. Okay. And if you do that, what you will find is that it is equal, and this is equal to half. Okay. This term here in the red, will tend to 1, because sine of a function, sine of a z is proportional to a z. Okay. Okay. So, because of that, this will turn out to be equal to 1. So, this is between, the integral is between 0 and 1. Okay. At 0 it is 0, at 1. Okay. So, at 1 this term here is basically sine of I minus j pi by I minus j into pi. Okay. This ratio tends to 1 as I minus j tends to 0. Okay. And I have this half outside. Okay. I have this half outside. So, the solution is equal to half for I is equal to j. So, this integral, if I take the function sine of I pi z multiplied by the function sine of j pi z, integrate from 0 to 1, it is always equal to 0 when I is not equal to j. Okay. And it is non-zero only when I is equal to j. Okay. It is non-zero only when I is equal to j. And for I is equal to j, it has this particular value of half. Okay. It has this particular value of half. Okay. So, this is often written as half times delta I j, okay, where delta I j is equal to what is called the Kronecker delta. This is equal to 1 for I is equal to j, and it is equal to 0 for I not equal to j. Okay. So, that is the solution. Okay. That is the solution you get when you integrate the left and the right sides, multiply the left and the right sides by, okay, sine j pi z, and integrate from 0 to 1. Okay. So, on the left side, when I carry out this, I will get summation of I is equal to 1 to infinity times delta I j by 2. Okay. So, it is I multiplied by some factor. That factor is 0 when I is not equal to j, and it is 1 when I is equal to j, or a half in this case when I is equal to j. Okay. So, all terms in the summation are 0 except when I is equal to j. Okay. And so, this entire summation just becomes A j by 2, okay, because all terms in the summation are multiplied by 0 if I is not equal to j. The only non-zero value is when I is equal to j. Okay. So, that is the left that is the term on the left side. We have to now evaluate the term on the right side and then calculate the solution of the equations. So, this orthogonality procedure I will continue in the next lecture for calculating the solution for the transient part of the temperature profile. I will continue this in the next lecture. I will see you then.